All right, so we're live here. So on example 3, remember what we're doing is we're trying to determine from an equation if we have an equation of a function of x, okay? And the ultimate litmus test, we said, was if you can solve for y as a function of x, and that is as a single equation, so that you have y equals and nothing on the other side pertaining to y. You just have x's and symbols and numbers. And you have to do it as a single equation. So on part A, we almost did that. We got y equals the square root of 6 minus 3x, which would be y as a function of x. The only thing is, remember, when you take the even root, square root, fourth root, you have to consider both plus and minus. And that gives you two separate graphs, which would reflect one across the x-axis and fail the vertical line test. So it didn't happen. So then we were trying to come up with some type of quick summary way to do it. And I said, look at the exponent on the y, right? The exponent on the y pretty much tells you, as we wrote up here, how many y values you're going to have for each x value. And to be a function, we can have no more than one. So if you ever see an exponent on the y that's bigger than 1, whether it's a 2 or a 3 or even a 1.5, chances are it's not going to be a function of x, okay? Now, there are some exceptions to that. So that's why I say if you can solve it for y exclusively, that's kind of the ultimate way to tell. But it kind of works, right? Let's try it out on example B. This equation right here doesn't have f of x in it, but just because it's not solved for y or f of x doesn't mean it's not a function of x. If we do our little quick criteria here, it would appear that I have y to the first in the first term and y to the first in the second term. I have two y's, but they're both to the first power. So what would y'all think? Do you think that this is a function of x or not a function of x?
Yes. Yes.
You would think that it's one or the other. Yes, good. Function yes or no function no? Yes. I would say yes as well. Y to the first, y to the first. So even though there's two y's, they're both to the first power. So I would say yes. Question mark? Let's go ahead and see if we can actually solve it for y as a function of x. Now, to do that, it's a pretty common little thing that we're going to do here. To be able to solve for y, I need to get y by itself. So how can I algebraically take two terms that each have a single y in it? Physically, it's written twice, and somehow end up with, in the end, just one y equals. How do I get from two y's to one y? Combine them? I could if they were like terms, but they're not like terms. Put it to the other side? Like just one of them? Like separate the terms? I mean, it would give us something to do, right? Like a waggle and a golf swing, you know? Combining them is a good idea, but they're not like terms. Separating them is not going to help us bring them together. But what do you notice, or what can we do if we have this term and this term, and there is a y that is common in both of them? Factor it out, right? F it. Factor it. Let's factor out the y from those two terms. That gives us 2x squared minus 8. Just from those two terms, yes? And now, Allie, that plus 4 doesn't have a y in it, so guess where I'm going to take him? I'm going to take him to the other side in the same line. So a plus 4 becomes a minus 4. There you go. So we'll collect the terms that have the y on the left, and then everything that doesn't have a y goes on the right. And I factored it out. And let's double check. If I redistribute, 2x squared y, boom, minus 8y, boom, plus 4 is now minus 4. And now I think we got it. To solve for y, I have to undo multiplying by this quantity, right? How do I undo multiplying? I divide. So I'm not going to show that step, but if I divide both sides by 2x squared minus 8, it divides that on the left, and I end up with y equals 7x minus 4 all over 2x squared minus 8. Now, the bottom can factor, but that's not really what our goal is at this point. Our goal is to see if we can solve this for y equals a function of x. A single equation. Did I do that? Y equals, and on the right side, I just have a function of x. There's no y's over here. It's just x's and numbers and symbols. Yeah. So we did it, right? We got it. So yes, this is a function of x. So now you can give it a name. Let's not use f. I'm tired of f. How about W for win of x, or Wenzel of x, or we did it of x, right? Whatever. Welcome to first period Precal of x. Winnebago of x. Okay, now I'm just getting way off task. All right. All right, so instead of yes question mark, how about yes exclamation point? All right. Okay, good. Yeah. All right, comments or questions on that one? Letter C. Whoa, look at that. We got y's all over the place. I have a y to the first over here, and I have a y to the first over here. We now know that that's not a problem. But we do have another exponent over here, y to the 3/2 power, or 1.5. You think this is a function, yes, or not a function, no? No, you're right, no. Because 3/2, which equals 1.5, is greater than 1, right? Now, what does it mean that you're going to have 1.5 y values per x? Well, that's a little bit hard to show. But know that it's not. You actually can't even solve for y. If you try to get your y terms on one side together and factor it out a y, you're going to be left with a little piece. You're going to be left with a half of a y in that. So it's algebraically difficult, if not impossible, to solve for y. So in this case, you look at the exponent, it's like, no. If it's bigger than 1, it's not going to work, right? It has to be 1 or smaller. All right, now look at letter D. X equals the square root of y. What do you think? Function, yes or no? No? Well, it's not y squared, it's y to the 1/2. Oh. So remember, it has to be 1 or smaller. Is a half smaller than 1? Yes. So my guess would be yes question mark, because 1/2 is less than or equal to 1. You can have no more than one output. Now, in this case, we can show what it means to have a half of a solution for every x value, because we can solve for y. We couldn't do that on the other one. How would I solve for y here? How do I undo raising something to the 1/2 power? Square it, right? Anytime you want to get rid of an exponent in a conditional equation, you just raise both sides to the reciprocal power. That's why squaring something that's square rooted works. Because what's anything times its reciprocal? 1, right? So if I do that, I get y equals x squared. All right? Now we know what the graph of y equals x squared looks like, yes? Yes, yes? Let's graph it. Y equals x squared is, hey, I'm smiling because I'm in a math class, and I'm also smiling because we're winning the play of the week. Now, there's one exception here. We know this passes the vertical line test, but that's not what the graph of x equals the square root of y actually looks like, okay? We can solve it for y to help ourselves sketch it, but we always have to consider what was originally given, all right? So if you look at it, this graph here, we have positive x's on this side, yeah? And then on this side, we have negative x's. Yeah? No big deal. If you look at the original equation, will x, in actuality, ever be a negative number?
Yes.
Well, look at it. If I look on the right side here, I have a positive 1 times the square root of y. I can't take the square root of negative numbers, right? That's not a problem. But if I ever take the square root of a positive number or 0, Will that number ever be negative? No. When I have it written like this, I have it written like y is the independent variable. So if you plug in any value of y, like 0, the square root of 0 is 0. So x can be 0. But x is never going to be negative because this is a positive square root. All right? So if you look at this original equation, x equals the square root of y, we know that x, oh, I will put a comma, x is always going to be greater than or equal to 0, always. So when we solve it down here, and we get y equals x squared, we just have to limit it to what the original statement requires. So what does that actually look like? Here's 0, and then positive x's look like this. So it's just the green graph, which is the equation x equals the square root of y. So that's kind of what it means to have only half of an output. We don't see the whole graph, but does the green portion of the parabola still pass the vertical line test? Yeah, it does. Okay. So that's why when you look at the equation, the exponent can be less than 1. It could be equal to 1 on the y. It just can't be greater than 1. All right. Okay, excellent, excellent, excellent. Now it's time to start doing some real stuff, okay? We're going to algebraically find domains now of things that we know to be functions. So here are the 3 things that will limit or restrict any domain of any function, okay? You've known the first one since like your first day in a math class. Your elementary school teacher probably had like a funny like commandment, right? Thou shalt not, murder, don't murder, and then don't divide by 0, right? Those are like the 2 rules of elementary school in a math class. Division by 0, can't divide by 0, still can't divide by 0, okay? Why is that important? Well, when we're trying to find the domain of a function, if we see a function that has a denominator with a variable in it, or an expression with a variable that's to a negative exponent, right? Because that's a denominator in disguise. There might be values of that variable that when we plug it in, give us a 0. And we can't divide by 0, so it's our job to find those values if they exist and kick them out of the domain club, all right? So we can't divide by 0. So in that case, we're looking to avoid a single number, 0. The second thing that we're going to be looking for algebraically is taking the eventh root, square root, 4th root, 6th root of a negative number. It doesn't work, right? The square root of a negative number is a complex number or an imaginary number. And we're talking about real numbers here. Same thing with a 4th root. You can't take the 4th root of a negative number. You can't take the 6th root of a negative number because when you have an even number of negatives, they pair up to become positive. Now, you can take the cube root of a negative number. That's fine. The cube root of negative 8 is negative 2. So why is that important? If you ever see a square root or a 4th root or something like that with a variable underneath it, or you see a fractional exponent like to the 1/2 power or to the 1/4 power or something like that, and there's a variable in that expression, there might be values of that variable that when you plug it in, give you any type of negative number, and we need to avoid those. Okay? So in the first one, trying to avoid a single number in the denominator. Can't divide by 0. But in the second one, we're trying to avoid a whole category of numbers, negatives. Those are the first 2, and those are the ones that we're going to be focusing on in this section. There is a third one later on when we study logs. We can only take logs of positive numbers. Okay? So we'll cross that bridge when we get there. So right now, can you remember 2 things? Division by 0 and square roots, 4th roots, even the roots of a negative number. You can remember that, right? 2 things. Not 3 things, just 2 things, right? I'm going to close my eyes. What's one of the things I want you to be on the lookout for? Division by 0, okay? And now I'm going to peek with one eye only. What's the second thing? Even root of a negative number. Now, truth be told, we're going to primarily be looking at square roots, right? But it could be a 4th root or a 6th root or even a 100th root, okay? 2 things. That's it. Keep that in mind as we move forward. As they get kind of spicy and you're like, oh, I don't know what to do. Just be like, take a deep breath. Two things. Trying to avoid two things. All right. Example 4. Let's try it out. How much time do we got? Plenty of time? 20 minutes. All right. Find the domain of each of the following. State your answer in set or interval notation. All right. I'll show you how to do that. So you walk up to this guy here and you're like, what's up? F of x. I know it's a function because it's got the name f of x. Yeah, and you can tell there's just x's and symbols and numbers on the right-hand side. Okay, so we're trying to find the domain. That is, what values of x when we plug in give us an actual output? Well, we're looking for two things. Division by 0, square roots of a negative. So, do I have a denominator? Yes. Is there a variable in it? Yes. So, I might have division by 0. I'll check for that. Do I have a square root or a fourth root in this problem at all? Is there a square root in here anywhere? Not a square, but a square root. No, there's nothing to the 1/2 power either. So, I don't have to worry about that one at all in this problem. The only thing that's going to concern me for this problem right now is the denominator. It's a quadratic. So, from your knowledge of quadratics, up to how many values of x possibly when I plug it in will make that 0? In other words, how many solutions can a quadratic have at most when you set it equal to 0? How many x-intercepts can a parabola have at most? 2, right? 2. Any polynomial of degree n, in this case is degree 2, it can have up to that many x-intercepts or zeros, okay? Beat the bot. We're still beating the bot till 7 p.m. today. All right, so here's what I want you to do. I'm going to go ahead and say denominator. Denom. I want you to always, when you have something like this, I want you to take your denominator and I want you to say that it can't equal 0. Because we're trying to avoid a single number, I want you to say the denominator can't be 0. We call that an unequation or a non-equation. And you can solve them just like equations, all right? Anytime you have a denominator, I want to see you set the denominator not equal to 0. Now, let's do that. X squared plus x minus 6 shall not, cannot be 0. Now, pretend it's equal to 0. In fact, I'm not going to count up even if you set it equal to 0. That's fine. I do want to see either an equation or a non-equation. If you set it equal to 0, that's fine. Just remember, you're trying to find the values that don't work, okay? When it's equal to 0 or not equal to 0, we need to solve it by whatting it? Factoring it, okay? So let's go ahead and factor this. This is an easy one. Keep it equal to 0 or keep it not equal to 0, okay? Either one, you choose. That's x, that's x. This is going to be plus 3, that's minus 2, guys. Double check, inside, outside, yeah. So now, you don't have to show me setting each of them separately not equal to 0 and then subtracting 3 and adding 2, okay? I would prefer you can just look at x plus 3 and say that x cannot be negative 3, and then look at x minus 2 and say that x cannot be 2, okay? That makes sense? And again, I don't care if you have equals or not equals at this point, because that's not your final answer, believe it or not. This is you just gathering the evidence. What we have to do now is fancy up our answer. We're trying to find the domain, so we're going to put big D for domain. And typically, if the function has a unique name like f or g or h, we put the subscript right here. So we call that D sub f. It just shows that it's the domain of f. We put a colon instead of an equal sign. Okay, we're not going to name the set. We're going to list the set. That's the difference. If you name the set, you can put an equal sign. We're going to list the set. Now, there's two ways to do it. You could do set builder notation. It would be the set of all x such that. Now, in set builder notation, you have a lot of flexibility. As long as you define the set, you can do it any number of ways. So the easiest way is just to say x cannot equal negative 3, comma, x cannot equal 2. Close the set. That's the easiest way. If you want to do it with inequalities, x is less than negative 3, comma, x is between negative 3 and 2, comma, x is greater than 2. That works as well. That's just a lot of writing. The default set of numbers that we use is the real numbers. So when you say it's the set of all x such that x is not these two guys and these two guys only, by default, that means that all the other ones work. Okay, so that's kind of a nice way to do it. That would be set builder notation, or you could say d sub f colon. You could do interval notation, which would look like this: x epsilon, x is in the interval, and now you have to go from least to greatest, right? Interval notation. What would be our starting position? No, that would be the one we have to step over. We're on the number line. What values work? What's negative infinity? Parentheses negative infinity. And then we cruise on the number line all the way until we get to -3. And like we've come across a cow patty, we just kind of step over it like this, you know, and we keep going. So how do we step over -3 without including it? Parenthesis, union, parenthesis, -3. That's how you step over a number without including it. And then we cruise from -3 all the way up to 2. Oh, cow patty alert. Step over 2. And once we get past 2, we're out of the cow patty field, and we can cruise all the way to infinity. Either one of those. Obviously, you're going to have a preference, right, on which one of those. And I don't care which one you write if this were a free response. On a multiple choice question, and again, we're shooting to test next Tuesday, or aiming to test next Tuesday. I might choose either one of these notations for an answer choice. So you should be able to read both of them, but when it comes time for you to present one of them on a free response, a short answer, or a quiz, you take your pick. And that's all we're doing right now. There are other things about this function that we can talk about, but right now that's kind of it. We call these two values discontinuities. I guess I will throw that term at you, okay? We call both of these values, we call these discontinuities. And the reason they're called discontinuities is because if you look at the interval notation, this graph exists from -infinity, and then all of a sudden at -3, at that single point, it's not in the domain. So there's some interruption in the graph, and we have to get to the other side of -3. And then it's continuous again. We can cruise all the way up to 2, and then oops, it's not in the domain. So now we have another break in the graph, a discontinuity again, if you will, and then we have to get to the other side. So those are both called discontinuities. Now, do you remember from Algebra 2? There's two main types of discontinuities, and we'll review them again here in a little while later. If you get to on a graph and it just stops and you have to get to the other side, it could be one of two things for now. It could be if I give you one, you think you can get the other? It could either be a hole, which would look something like this, right? We put a little open circle to show that a point is missing. That's actually called a removable point discontinuity. Or, what's another one? Very good, yeah. A vertical asymptote. A vertical, and here's how you spell asymptote. I call those VAs for short, right? You can abbreviate them VAs as long as you don't get it confused with the Veterans Administration. They do good work too. But a vertical asymptote, we denote like this, right? And what the graph does there is it like goes up to infinity on one side and possibly down to -infinity on the other. Beat the bot. So we'll talk about which one is which later on. But right now, we're just concerned with finding the domain. Okay? Those two discontinuities, they could actually both be holes. They could both be vertical asymptotes, or we could have one of each. There's really no rule on how many each is supposed to have, okay? All right. Any other comments or questions on this one before we mosey over to number 2, which is actually B? All right. Well, then you kind of know what to do. Letter B is yours. You do B on your own. Use A as a model, as a guideline. If you're already done, you're done. beat the bot if you're done, but go ahead and find the domain of g of x. Well, as we saw, like on the previous example, if you simplify it, if you ever simplify something to help you sketch the graph, you have to always go back to the original function to talk about what it actually looks like. So simplifying can help you collect information, but we always want to talk about the original function. So that's kind of an esoteric clue right there. Also remember, if you're working straight down, you need to keep your equal signs. Remember, the instructions on this problem is not to simplify. The instructions on this problem is to find the domain, okay? Find the domain. You can do it, you can do it. Beat the box, you can do it. Those of y'all who retested this morning, busy day today. I will try to get those graded during lunch. Whatever I don't get graded after lunch, I have an advisory math club meeting today during advisory. If you want to tell your advisory teacher and show up, it'll be in this room. We'll have passes eventually for that. But we're going to meet every other Wednesday. Today's the day. And then after school, I have an AP meeting in the library. And then I got to go home this afternoon and get ready for the pep rally tomorrow, as I know a lot of y'all do too, right? Stretches, calisthenics, costume, gather your costume up, because tomorrow's Western Day, Canal County Fair. It's going to be a great day, but a busy day. But I'll get your tests regraded. If you haven't retested yet, because we've talked, you can come see me. If you're retesting after school, I won't be in the room. I'll have to leave the tests for you on that back desk over there. But I've already talked to a couple of y'all. Beat the bot. Okay, so 300 one day, 600 the next day. Are you going for 1,200 votes yourself today? Or are you trying to double your output every day? Yeah? You're trying. Okay. All right. That's awesome. Dedication, devotion, turning all the night time into the day. You sing a song about sweet love woman. You do the song about the night. Baby, do the walk, do. You do the walk of life. Hey, you do the walk of life. What song is that? Who sings that song besides me? Dire Straits. Very good. Mark Knopfler. Nice. Nice. All right, here we go. G of X, G of X, G of X. You walk up to it. What's up, G? G money. All right. Two things, right? We're trying to avoid division by zero. We're trying to avoid square roots, fourth roots of negatives. Do we have a radical or a fractional exponent in this problem? Do we have a square root or a fourth root or a fractional exponent? No. So we don't have to worry about that. Do we have a denominator or a negative exponent? We don't have a denominator? Yeah, we have a denominator, right? And in the denominator, I spy a variable. If the denominator didn't have a variable, then, you know, as long as it's not zero, we're good. But I have a variable in the denominator. So there might be values of X that when I plug in, give me a zero. We need to avoid those. Now, you can probably look at that and tell what they are, because X squared is the difference of squares. But I want you to show this for now. I want you to say X squared minus 16. Here's another way to do it. If you want to say equals 0, we'll do it that way. And now we're finding the values that work. Now, there are two ways to solve this. Okay, I'll show you. The first way is to factor it, right? X minus 4, X plus 4. And once you set it equal to 0 or not equal to 0, you got to keep it equal or not equal to 0. And then this gives you X equals 4, comma, X equals negative 4. All right? So without the not equals there, that's fine. We just have to remember what we're doing. We're saying that these two values, because they give us 0, are now the ones that we don't want. Now, the other way to do this one, because there's no X term, there's no linear term, you could actually solve this one by separating, right? There's kind of another rule of thumb. You don't always have to factor if it's equal to 0. If you only have one variable term, like we have here, you can separate it. Get your variables on one side, get your numbers on the other. Now, this method sometimes leads students to only getting half credit because they forget to do something. I would have to extract the square roots now by taking the square root of both sides. What's the square root of 16? 4 plus or minus. And you think anyone ever has forgotten plus or minus? Yes, okay. So you have to remember not to forget anytime you are taking the square root of something, or anytime you are taking the fourth root of something, you have to consider plus or minus. If the square root is already there, you know, like it was up here, then you just take the indicated root, right? This square root was already there, so I was just taking the indicated root. But if we're doing it to solve, we have to do plus or minus. So anyway, those are the two values, right? Now, you can factor the top and one of them divides out, but that's not what we're trying to do right now. We're going to state the domain. So here we go. The domain of G is the set of all x's now such that x ain't not equal to plus or minus 4. Yeah. In set builder notation, again, you have a little bit of flexibility. You could say x cannot equal plus or minus 4 because that builds the set. As long as there's no ambiguity as to what the set is, we're good. And then again, by default, all the other real numbers work. Or if you like the interval notation, d sub g colon not equals is going to be x epsilon. And now, where do we start? Negative infinity with the parenthesis. And we cruise all the way up until -4. And then like a cow patty, we step over it. Parentheses, union, parentheses, -4. And then we cruise all the way up to beat the bot, 4. Step over the next cow patty. And then we cruise to infinity. Boom. All right? Either one of those. Doesn't really matter which one. Okay? Again, for the interval notation, having x epsilon keeps it in the context of a domain, x values. Okay? Because without that, look at that middle interval. It looks a lot like an ordered pair, like a point on a graph, an x and a y coordinate. All right, yeah. Now, those are two discontinuities. Kind of looking ahead, just a preview of coming attractions. Look what I could do with g of x if I did want to simplify it. I could factor a 3 out, and that gives me an x plus 4. And at the bottom, of course, I know that's x plus 4 times x minus 4. If I wanted to simplify g of x, could I? Yeah, what happens with the x plus 4s? They divide out, and I'm just left with 3 over x minus 4. But here's the deal. Because it's a function, not just an expression, if you divide out the x plus 4, you need to put a comma here and say, oh, and by the way, don't use -4. We still know that we can't use +4 because it's built in, right? When you plug in a 4, you get 3 over 0. It doesn't work. But notice that with the x plus 4 factor gone, you might think that you could actually plug in a -4. That would give you 3 over -8. That's not good. Okay? Now, we're going to learn later that because the x plus 4 factor divides out, that is, you can remove it from the equation. You can remove it from the equation. At x equals -4, which is the root of that factor, we are going to have a removable point discontinuity, also known as a hole. And because the x minus 4 factor has to stay, cannot be removed, its root, x equals 4, is called a non-removable infinite discontinuity, also known as a vertical asymptote. Excellent. All right. So 7 p.m. is the deadline for voting. If you can in your classes, let's beat the bot. Let's beat the bot. We don't want to give them any chance of a final 11th hour surge, okay? Have a great day. Western Day is tomorrow. See y'all later.